Welcome to Lecture 8, which is the final lecture on this short course on computational fluid dynamics. The subject of this lecture is the problem of turbulence and how practical turbulent flow simulation is carried out. In this first part of Lecture 8, we're firstly going to recap the origin of turbulence. We'll remind ourselves that all shear flows possess the property of rotation, and we'll see that turbulence occurs once this property can no longer be suppressed by fluid viscosity. We will see that there are three main approaches to solving turbulent flow problems. The first is to solve the Navier Stokes equations on a suitable finite volume or finite element mesh. This may sound simple, but there's a very significant computational problem to overcome, which results in having to use a very large supercomputer to solve a rather simple problem. This method also produces immensely fine detail, orders of magnitude more than what is required to solve an engineering problem. The second and third methods that we'll examine are both approximate methods. You will have already seen one of these methods before, which is that of the Reynolds Averaged Navier Stokes approach, or RANS. We're going to recap the key assumptions used in RANS, but we'll also outline another method, that of Large Eddy Simulation. So let's start by reminding ourselves what a challenge turbulence is. Up until this point, we've examined the solution to the Navier Stokes equations. In last lecture, we looked at how we decompose the Navier Stokes equations into a suitable numerical form, and then we outlined the simple algorithm that we can use to solve them. Now, don't forget that this method will only work on its own for flows that are laminar, where turbulence doesn't exist. And if we think about laminar flows, you've got two classes of laminar flow. You've got creeping flows, where inertia is negligible, very, very low Reynolds numbers. Then you've got inertial laminar flows, where the Reynolds number is significant, maybe order a few hundred, or even high few hundred, 800, 900. When you have inertial laminar flows, you will start to see interesting flow structures form when the flow geometry permits it. However, as soon as we exceed roughly 1500 or 2000 Reynolds number, depending on our flow geometry and depending on the physical conditions, our flow will suddenly trip to being transitional and then turbulent. And at that point, life becomes a heck of a lot harder because we have random, chaotic vortex motion dominating the flow. There are two quotes that I'd like to give you that concern turbulence, both of which that I think frame the problem that it poses very, very nicely. The first quote was due to Richard Feynman, who of course was a Nobel laureate in physics, and he said that turbulence is the most important problem of classical physics, which is a really significant statement to make. Another very significant statement was made quite some time before Feynman's statement by Sir Horace Lamb, and Sir Horace Lamb was a Fellow of the Royal Society in the UK and also one of the early hydrodynamicists. And he said this: "I am an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is the turbulent motion of fluids. And about the former, I'm rather optimistic." So, I think that effectively summarises that turbulent flow is hard. Now, let's see why we have turbulent flow. Because when one thinks about it, at a superficial level, it seems rather miraculous that you start with a laminar flow, which is a beautifully well-ordered flow, very easily mathematically described, no chaos, everything perfectly predictable. And yet, if you just make it flow a little bit too quickly, suddenly, it seems, the flow just decomposes into random chaos. And we need to understand why this happens. Now, we're going to understand this by a simple illustration. On the whiteboard here, I've put a schematic diagram of a flow geometry. It's in 2 dimensions. You can imagine this to be a cross-section through a pipe or an infinitely wide slit. Now, we're going to start off in laminar flow, and there on that flow domain I have sketched a velocity field for laminar flow. It's nice and parabolic. We've got no slip boundary conditions on the upper and lower wall. Both of these walls also happen to be stationary, and so the tiny layer of fluid next to these walls is also stationary. And then the fluid velocity increases in a parabolic nature until you have a maximum on the centre line of the geometry. Now, let's examine a little element of fluid in the lower part of this flow, below the symmetry line. And we'll sketch in this blowout here what the forces and stresses are acting on this element of fluid. Because our element of fluid doesn't sit on the symmetry line equally top and bottom, then we have an asymmetric set of shear forces acting on the upper and lower surface. And you will expect, if there's shear on the upper and lower surface imbalanced, that there will be a net moment as well to counterbalance that. And so that's what we find. And this is an important point. And the important point is this, is that if you have a shear flow in laminar motion, rotation is an inherent property of that shear flow. Now, moreover, we can actually quantify how much rotation we've got by something called a vorticity vector. Now, vorticity, written omega in this expression on the board, is the curl of the velocity field. Now, if you remember what the curl of a velocity field looks like, if we have a velocity field having an x direction velocity u and a y direction velocity v, then omega, the curl of the velocity field, will have 0 components in the x and y direction, but it will have a non-zero component perpendicular to both of those directions in the z direction. And so looking at this diagram, if we have our x direction aligned with the flow direction, and our y direction aligned with the height of the slit, or the diameter of the pipe, then the z direction is into the board. So the rotation axis would be into the board, and so what you would see is swirling in plan view on that diagram. So what you have in your data book are expansions of the vorticity vector on page 26 in all 3 major coordinate systems, which is of great assistance if you need to do vorticity calculations. Now, that's for laminar flow. Simple laminar flow in shear will have rotation as an inherent property. So let's keep our shear flow and let's just gradually increase the Reynolds number and see what happens. Well, if we keep our flow geometry and material properties the same, then increasing our Reynolds number means increasing our flow velocity, which means we start to stretch our velocity field like so. So as our velocity field stretches, we can perhaps see that that force imbalance, that shear stress imbalance on our element of fluid gets greater and greater and greater. Let's examine this most stretched velocity field and look at what the force imbalance looks like on our element of fluid in 2 locations. Let's look firstly close to one of the walls, and this is where we're going to see one of the greatest shear stress imbalances. And so the moment induced on a fluid here is going to be very, very great. If we look closer to the symmetry line, the imbalance is going to be less, and so again the moment will be less. Now, if we keep stretching this velocity field, at some point rotation is going to win. And what you find is that rotation will win in the point in the flow where that shear stress imbalance is greatest, which is going to be close to a wall. And so when we hit that magic Reynolds number, somewhere between 1500 and 2200 depending on our geometry, rotation wins at the wall of the geometry. And what happens is a vortex is born at the wall. A vortex is described as being shed. And as soon as the first vortex shed, the act of shedding a vortex triggers other vortices to be shed as well. And so what you have is this domino effect where the shedding of the first vortex trips another vortex, which trips another vortex, which means in an incredibly short space of time, your entire flow becomes turbulent. And so maybe when we think about laminar flows in terms of this inherent property of rotation and how this property is suppressed by viscosity, but how with sufficient inertia that property wins, we can maybe see relatively naturally in our mental model how turbulence actually starts to happen. Now, let's think how we might describe this vortex motion, because as we've seen, turbulent flows are challenging, and understanding how turbulence works and modelling how turbulence works is a very important thing and a very hard thing. Well, there is one equation that will adequately describe all turbulent flows, and it is this equation here. Looks familiar, doesn't it? It's the incompressible Navier Stokes equation, with the caveat that we're talking about an incompressible flow in this case. But if we think about what's happening when you have vortex motion, all you've got is momentum conservation. And for an incompressible Newtonian fluid, the Navier Stokes equations written in this form describe conservation of momentum. And so we should, in theory, be able to describe all of turbulent flows just simply by solving the Navier Stokes equations. And indeed we can do that, but there's a subtlety here, because if we think about what's happening within the flow, we want to be sure that we solve the Navier Stokes equations such that we've got enough resolution to actually resolve all these different flow structures. And when that first vortex is shed from the wall, actually it's very, very, very small. And so if computationally we want to resolve that vortex in sufficient detail to be able to not only describe it, but also to predict how it will affect other parts of fluid and trip turbulence in its own right, we need to ensure that we've got a very fine resolution indeed. Now we can make estimates of the resolution both in space and in time that we need to do this, and this is by referring to something called the Kolmogrov microscales. Now, the Kolmogrov microscales can be written as I've just put them on the board here. We've got a length scale, L, which is the length scale of the smallest vortex. We've got a time scale, T, which is a time scale of the smallest vortex. And both these length and time scales can be related to the kinematic viscosity of the fluid and something called an energy dissipation rate. Now, we can estimate an energy dissipation rate in turbulent pipe flow using this expression here. It relates to our friction factor, a pipe diameter, and the fluid velocity. So let's make some estimates as to what these length and time scales are for a simple turbulent pipe flow problem. Imagine that we have water flowing with a superficial velocity of about 1 metre per second in a pipe that is 20 millimetres in diameter and about 10 centimetres long. Let's also say that our flow is turbulent and our Reynolds number is about 20,000. So we first of all need to estimate the energy dissipation rate, and so we can do so by knowing our friction factor CF, and if we use the Blasius equation where CF is 0.079 Reynolds to the minus a quarter, we can estimate what epsilon is. Furthermore, once we know epsilon, we can work out our Kolmogrov length scale and our Kolmogrov time scale. And for this particular problem, we find that the Kolmogrov length scale is roughly 51 micrometers, and our Kolmogrov time scale is about 2.6 milliseconds. So 51 micrometers is roughly the diameter of the smallest vortex. Now, when we consider a vortex motion swirling around, it's like a miniature hurricane, we will need quite fine resolution to capture that motion sufficiently. So if we think about a 51 micrometer diameter vortex, we would need, from a computational standpoint, enough mesh cells within that vortex to actually describe that fluid motion with accuracy. So let's make a very crude assumption that the largest grid cell that we want in our simulation is roughly 10% of the Kolmogrov microscale, and roughly the largest time scale is going to be about 1/10 of the Kolmogrov time scale. When we work this through, that means for this rather simple engineering geometry, a turbulent flow in a pipe, we need about 3 times 10 to the 11 finite volume cells, and we need to time step our Navier Stokes equations at about 260 microseconds per step. Now, what this means is you need a very large computer. We will see in a minute how long a problem of this nature would take to solve on a major supercomputer. But the key message here is that 3 times 10 to the 11 grid cells for turbulent flow in a pipe is probably of order 10 to the 6 or 10 to the 7 more than what you would need using other approaches. The approach that we've described is called direct numerical simulation. It is used widely as a research tool, but currently it is impractical for engineering use. Let's illustrate why. So, direct numerical simulation is effectively solving the Navier Stokes equations on incredibly fine grids at incredibly fine timescales. And what it will reveal is the exact structure, as it devolves in time, of every single vortex in the flow. And so it can give you unprecedented insight into the physics of the flow. Absolutely fascinating. It can be used to improve and inform other more approximate methods of turbulence modelling. But by itself, it gives a lot of detail, very, very huge amounts that are unsuitable for engineering use. And if we think how long these simulations take, a few years ago, in 2017, a large-scale direct numerical simulation was carried out using about 2.4 times 10 to the 11 finite volume elements, which is not that dissimilar from our 3 times 10 to the 11 volume elements for our example of a turbulent flow in a pipe. Now, at that point, the Myra supercomputer was number 11 in the top 500 in the world. It had a compute speed of about 8.6 petaflops, and this simulation took several months to achieve. So, using very, very heavyweight computing, direct numerical simulation takes an incredibly long time. Now, as computing power increases, we're already into exascale computing these days, and we would expect the contribution of direct numerical simulation to increase substantially, but it is still unlikely to be a practical tool for engineering flow simulation for many years yet to come. So we need another approach, and one of the earliest approaches to be developed was down to Osborne Reynolds. Now, Osborne Reynolds, of course, gave his name to the Reynolds number, and the methodology that we're going to examine is Reynolds Averaged Navier Stokes, or RANS. You will have come across this method before. For those of you who have sat the chemical engineering tripos at Cambridge in 2A, you will have seen the RANS approach, and you will have used Prandtl's mixing length theory to evaluate some of the parameters that drop out of that approach. Now, the Reynolds Averaged Navier Stokes approach says something actually very elegant. It says that a velocity of your flow, u, can actually be decomposed into two parts. You've got a steady average velocity, u bar, and then random instantaneous fluctuations, u dashed, that are time dependent, so it becomes u dashed of t. Now, when you substitute that expression for velocity into the Navier Stokes equations, what you find, after a little bit of mathematics and implementation of averaging laws, that an additional term appears in your Navier Stokes equations. It's called the Reynolds stress. And that means that you now have more parameters than you have equations to solve for. And so hence what you need alongside your Reynolds Averaged Navier Stokes equations is a turbulence model. Something that provides an additional equation to sufficiently describe the problem, or what we term close the problem. Now, there is another approach that is a hybrid between the Reynolds Averaged Navier Stokes approach and the direct numerical simulation approach, and that is the approach of Large Eddy Simulation. Now, what we do with Large Eddy Simulation is say that there is a certain size threshold above which we will directly model the vortex structure. And exactly where that threshold is set will depend on the compute power that you've got and the level of detail you're looking to resolve. Below that threshold, you will use closure approximations similar to those used in Reynolds Averaged Navier Stokes to figure out what's going on the very, very fine level of detail down to the Kolmogrov microscale. Large Eddy Simulation has been used routinely in computational fluid dynamics for some years now, and can give some very, very accurate results when applied to the right problem and when tuned in the correct way. It's more computationally intensive than Reynolds Averaged Navier Stokes alone, but it's interesting to note that for some engineering problems, Reynolds Averaged Navier Stokes, when tuned in the correct manner, can perform comparably well. So, the key to all of this is to always apply an appropriate level of analysis to solve the problem in question. You don't need to do direct numerical simulation to figure out properties to do an engineering design. You need direct numerical simulation to understand the incredibly detailed and complex flow physics that's going on, maybe to develop a new turbulence model. Likewise, don't default to Large Eddy Simulation thinking it's going to be better because it directly models vortices down to a certain size scale. A well-tuned Reynolds Averaged Navier Stokes model may be quicker, may give you a comparable level of detail for engineering use, and may be significantly computationally less expensive. And so, from an engineering standpoint, use the appropriate level of modelling and simulation that is fit for your purpose. Let's recap a few key points. We've seen that all shear flows have vorticity as an inherent property. Laminar flow ceases when the stresses due to vorticity overcome the effect of viscosity and you end up with chaotic turbulent flow. We've seen that actually from a standpoint there is nothing special about turbulent flow and describing it because all it is momentum conservation. The challenge, however, and it's a very significant challenge, is that in order to do so, you need to solve the Navier Stokes equations at resolutions below the Kolmogrov length and timescales, which is the approach that direct numerical simulation takes, which requires very, very large supercomputers in order to solve relatively simple problems. There's two practical engineering approaches, Reynolds Averaged Navier Stokes and Large Eddy Simulation. Of these two approaches, we're going to be looking at Reynolds Averaged Navier Stokes in far more detail in the next part of this lecture.